Awesome. Well, thank you and welcome this morning to the Databricks Data and AI Summit and to the talk on Project Alexandria from the Department of Energy. For those of you that are relying on the closed captioning, if I am speaking too fast for it to pick up, please let me know so that you're able to enjoy the presentation. A quick note for all of you, if after the presentation you would fill out the survey that you can find through your app, I believe they might also email you. That helps not only the Data and AI Summit put on an amazing event, but it also helps me as a speaker improve and make sure that I'm presenting what's most important to all of you. So who am I? My name is John Darrington. I am primarily a software engineer and architect. I work primarily with large distributed systems of scientific data. I've worked with nuclear reactors. We built the first ever digital twin of a live nuclear reactor, the AGN-201 out of the Idaho State University. I helped design and develop an open source data lake called Deep Links for the Idaho National Lab. I have two little boys, an 8 and a 3-year-old, who would love to be here today. I don't know that I would love them to be here, but they would love to be here. And I enjoy 3D printing. My personal site and GitHub are there. Please keep in mind they do not reflect the opinions of my employer. And who is my employer? It's the Idaho National Laboratory. It's a Department of Energy funded laboratory. We are 75 years old, and we ran the first ever city in the United States on nuclear power. That was us. We ran that. We have over 6,000 employees that work in the clean energy spaces. We work with hydrogen, renewable resources, nuclear. And if you want to have a fight about nuclear being clean energy, you can talk to me after the show. But we can't have that discussion. I think it's a really important discussion to have, especially now. The campus at Idaho National Lab is the size of Rhode Island. We have a very large space out in the Idaho desert where we have a test bed. We have in-house offices. I work remotely out of central Maine. So we have employees scattered all across the United States, and we also employ a lot of individuals across the multiple different nations. We have a $1.6 billion budget, which might seem small, but for a Department of Energy lab, and especially in the middle of Idaho, is actually pretty decent. Before I talk to you about what Project Alexandria is, I want to talk to you a little bit about how Idaho National Lab found Databricks in the first place. Because we only really started getting involved with Databricks and Databricks technology roughly a year ago, around this same time. I came to the Data and AI Summit for the first time last year after having finally found Databricks and getting involved with a lot of the technologies. And the way Idaho National Lab found Databricks, and you might already see this coming. For those of you that aren't familiar, that is the little crab is the Ferris. It's the mascot of the Rust programming language. And then the icon to your right is the Delta Lake icon or logo. And we were looking at the time for a efficient data storage pathway for our open source data lake. We were storing scientific data, and in particular, we were storing spectrometer data, which is structured data, but it's millions of rows, even for a small data set, and more importantly, millions of columns, or sorry, not millions of columns, thousands of columns. At the time, we were using timescale DB on Postgres, and then some of you already might see where this is going. Postgres has like a 1,600 column limit, and so trying to put spectrometer data with 2,600 columns of data into a 1,600 column limit database wasn't really working. We were looking at having to chunk the data. Thank you, you got that. We were looking at having to chunk the data, move it across different tables, or combine it, which kind of took away some of the efficacy of that. We were also running into licensing concerns with timescale DB on Azure's Postgres instances. We didn't have access to a lot of the aggregation functions that we needed. And that's when we found Delta Lake. And this talk is marked as a beginner's talk, so I will spend just a brief moment. Delta Lake you can think of as Parquet on steroids. It allows for ACID transactions on Parquet files in object storage. It is a fantastic tool for storing large amounts of data, for manipulating that data, and being able to do things like time travel, rolling it back, and maintaining it in a better format and in a better structure than simply throwing Parquet files or CSVs. In this case, these are all CSVs onto object storage and then forgetting about them. And you have to understand that in the Department of Energy, for a long time, state of the art was literally, let's throw all of our data from a project onto a hard drive and ship that across the states to another lab. That's state of the art. And so we're moving on from that. So Project Alexandria is a data management platform. And it was funded and created by the NNSA, which is the National Nuclear Safety Administration. I always mess that up. I want to say non-proliferation, because that's what we're doing inside the NNSA. There's a typo here. It's built for the modular management and search of projects and ventures data across the non-proliferation space. And for those of you not familiar with non-proliferation, it's basically the practice of making sure those countries and nation states that have nuclear power don't develop nuclear weaponry, or nuclear adjacent power develop nuclear weaponry, or nuclear fuels for nuclear weapons. And so it's an extremely important field of study and understanding to help keep the world safe and to help keep ourselves safe as well. The Project Alexandria platform is a collaboration across over 7 different national laboratories in the Department of Energy space. Some of those are the Sandia National Labs, Los Alamos, Lawrence Livermore, NETL, Pacific Northwest, Oak Ridge, and Brookhaven, to name a few of those. And we at Idaho National Laboratories are leading this effort, and I am the lead architect on this project. So the core platforms for our project, and we'll go left to right here, you can see first that we are built on a foundation, and the closed captioning is kind of cut off the Databricks part, but we are built on the foundations of Delta Lake and Databricks. But we have platforms that we are using that are built on top of these technologies. To the first on your left is the Ingest platform. This is an open source tool that was developed by Idaho National Labs, which we'll talk about in just a minute, for the collection of data and metadata, which is extremely important in our field. The Lake FS, which is like a Git for data, and we'll have a slide on each of these in just a moment. And then Acryl's Data Hub, which is a metadata catalog with the ability to connect pieces of data as on a graph, which is really important for the interconnectedness we needed between projects and ventures. One of the biggest concerns that Alexandria hopes to alleviate inside of this space has to do with the siloing between projects and ventures in the NNSA non-proliferation space. Standard operating procedure is very much project starts, they generate tons of data. That data then at the very end gets shoved into some kind of data storage medium, be it a hard drive, be it something in the lab, be it an HPC cluster, and then everyone else goes on with their lives. And that data may sit there, but everyone else has moved on from the project. There's no steward of that data unless it's been written into the project's funding. And so that data can just either stagnate or disappear. And so one of the things that Project Alexandria hopes to achieve, and the reason we chose some of these tooling, is to ensure that we have that data interconnected and we have stewards for a long-term view of this data over time instead of stopping at the end of a project. So that's one of the most important things. So we're going to take a look at each of these 3 core platforms very quickly. The first is the Ingest platform. Ingest is currently in a pre-release state for open sourcing. You'll be able to find that at the inlsoftware.inl.gov or on the Idaho Lab GitHub when it open sources in the next month. It's designed kind of like Box, where we have a very nice UI for dragging and dropping files, but we also enforce the collection of metadata. We have dynamic forms. We also have the ability for users to upload their data and then supporting data along with it. and then request those across inter-department boundaries, inter-organizational boundaries from our university partners. It's all built in mind of taking this data, collecting the metadata, the important information that might not be contained inside the Parquet file or the HDF5, because we might need to know where it was collected, when it was collected, what project it belongs to. And in reality, a lot of the times, the way they hold onto that data is with file structure. So how do you know what project this came from? Well, it's in the file Sapphire. Oh, that's great. That doesn't help us. That could easily have moved from a different project. And so you have a lot of inconsistencies in the data that we are trying to get away from. And what ingest does is it takes that data and it writes it out to Delta Lake and or JSON, depending on if you don't need to use that technology, and writes it out to object storage. And those object storage could be S3, Azure Blob, or Azure Gen 2 Data Lake, or GCP's offering in that realm. Or you can write it off to on-premises operations that expose an S3 AI or API like Ceph or MinIO or Versity. So ingest is a very important part of the platform because that's where the data flows in. But last year, I remember sitting in a presentation for LakeFS and thinking to myself, hey, this is really neat. Because they were explaining that LakeFS is like this GitHub for data, like the ability to branch and roll back and to curate your data while at the same time being the source of truth. So you throw this on top of object storage, and suddenly you have the ability to version and to work with this data as if you were in a GitHub repository, as if you're working with source code. And these are multi-gigabyte, terabyte files that you're dealing with. And it just works very well and very fast. And this was extremely important to us to provide a staging area because we didn't want people to come in and say, oh, here, I'm going to drag and drop my data, there it is, and stop there. We only catalog the data that's on the main branch of a LakeFS repository. So like the main branch of a GitHub repository, we only look at the data on the main branch. So unless your data makes it there, it's not going to happen. And ingest integrates with LakeFS, opens up its own branch, so you have to have another step where a curator or the data steward goes in and has to figure out, okay, is this data something I want cataloged? Does it need to be normalized? Does it need to be classified before we take it and catalog it? So LakeFS plays a huge and very important role in making sure that our data is curated and managed at that certain level. Last but not least is the Data Hub platform. Again, this is owned currently by Acral Data. It is an open source project originally developed by LinkedIn. It is a metadata catalog platform that allows you to make a lot of connections between the data. It holds on to things like data lineage, which is extremely important to us because we might be creating result sets for ML models that we need to know where they came from in the first place. Not only that, but that lineage can be extremely important for figuring out classification of data. One of the things we haven't talked about yet, but we will, is one of the biggest problems in dealing with the government's data is its classification, whether or not it is unclassified data or official use only or unclassified confidential information. There's a whole skew of classifications that you have to manage. And especially classified data, you have to be very, very careful not to generate classified data, and we'll talk about that. But once we get the data into our system and we have it in the catalog and we have it interconnected and we have LakeFS, and in this case, we actually augment a lot with Azure services like serverless functions. Data Hub doesn't let you download the data directly from the catalog. You either have to have a pointer and follow it back. We augmented the catalog to allow direct downloads from it. And integrated the LakeFS S3 layer in order to provide for a much easier pathway for downloading. Because at the end of the day, we're dealing a lot with data scientists or just scientists in general that don't even call themselves data scientists. And they want it to be as easy as possible to get that data back out. You're not going to get them to download an API key in secret and write a script or download this piece of software and enter their API and key in secret. So you have to be very, very careful with how streamlined you make this process for them. So now that we have the data, what are we going to do with it? We have it in our system. We have it ready. Yes, we're going to make it searchable, but that's only part of the battle. That's the only part of what we wanted to achieve. And that's a big achievement in the DOE space. Making something searchable, making it so that ventures and projects don't repeat themselves, that they're able to find and build on the foundations of a previous project is huge. But we wanted to take it one step further and move up the chain, so to speak. So the data, before it can be useful to things like AI, in this case, that's what we want to build, is we want to look at retrieval augmented generation and look at building LLMs or chatbots to help users not only find the data, so finding the data is important, but be able to draw conclusions and connections between pieces of data that they might not have thought were related, or that we might not have thought were related. Because one of the powerful things about dealing with vectors and vector databases and generating the contexts you need to train AI is that you are creating a context that you don't fully understand. I've rarely met anyone that can look at a data set and understand all the contexts involved with that data set and understand how it interplays with, this seismoacoustic data interplays with this weather data. Very few people can keep all of that in their head. And so you need to have a way to represent that in code and in data. And that's where the vector database comes in. And so what we do is we take the data, the metadata from LakeFS, and the information about how it's connected from Data Hub, and we write a new Delta Lake table that we use as a foundation for vectors. And this is where I have to get a little hand wavy, not because it's a beginner's talk, but because what we're doing is proprietary at this time and I haven't had the permission to expose it yet. We are planning to open source it. We currently have a CLI tool that we are using to take these vectors and work on generating models. But because of the classified nature of the information, I have to be just a little hand wavy here, so I apologize for that. But what I will say is that we have to get a lot out of those vectors in order for them to be important for us. One is this pre-filtering step that we can do both in the vector, the now general access vector search from Databricks, as well as just getting the data to become vectors in the first place. But we have to pre-filter them because that last part there, the manage of classified data. One of the biggest issues we'll face, and I'll bring it up again at the end, is the fact that the equation classified data equals classified AI models is easy to understand. Everyone can agree and accept that. But unclassified data can also equal a classified AI model when combined with other unclassified data sources. And let me bring up an example. Let's say we have an experiment that took place out in some desert, and we've scrubbed the information about where it took place. And the information we have now, which is unclassified, is seismoacoustic data, some video files, and then weather data. Well, let's say I combine those pieces of information, feed them into a model. There is a high probability that the model can posit where that experiment took place and generate classified data from all of these unclassified sources. By putting labels on things, by combining them, by making these contexts, we run into a problem all the time, and DOE is very, very aware and very scared about it, for good reason, of generating a model that can give out classified information. And if somebody gets hands on this model, they can find more information out than we were willing to give in the first place. The second part here is we can use those vectors and do the training without involving these individuals in the training. Remember, I talked about the standard operating procedure for projects, do all the data, and then move on. Unfortunately, in the DOE world, and in a lot of places around, are very project or funding driven. And so if you don't have a project to bill, and you call up, let's say, Bob in accounting who worked on this project 5 years ago, there's a very real chance that he's going to ask, hey, what's funding this? And if you can't give him a way to fund it, he can't give you his time. And so you lose intrinsic information about the data. And so being able to get the data beforehand and generate a context which can be reused over and over is extremely important to Alexandria, so that even as these people move on and have the best intentions, that I made Bob seem kind of like a jerk, but it's not always the case, we need to be able to move on without them. And then the last part is, because we're using Delta Lake and because we're using that as our storage medium, we can work without Databricks if we have to on classified networks where we might not have access to it, or on on-prem situations where we don't have access to the Databricks platform itself. I am so happy and grateful that Databricks has gone I think, a very intelligent route in open sourcing Delta Lake and open sourcing the foundational technologies, because then we can augment with Databricks, but then pull back down if we have to in these classified networks. So it's extremely important for our work. So to recap the data use timeline, we have users that upload their data through the ingest platform. And again, they might be using things like CP, very large distributed file copying for these terabyte datas. We're working on standing up a Globus node. For those of you that are familiar with Globus, it's not my favorite tool, but it works. Once that data is pulled into LakeFS, it's curated. And we have, each of the project adventurers have to give us what's called a data owner to curate that data and accept it for use, if they're still around. If not, then the Alexandria team is in charge of that. That data gets sent to Data Hub, and really this is a typo, it should be metadata sent to Data Hub, because the data itself stays in object storage. We really are trying to move this data as little as possible, because when you're talking about cloud, compute is expensive, but data transfer costs are what can get you in trouble a lot of the time. Egress costs, and then transfer between regions or transfer between cloud services is really hard. That metadata and data is written out to Delta Lake. Again, so I'm sorry, some hand waving here. We generate vectors, we put them in context, and we train some AI. It's really a neat, interesting step. I'm excited for it to come fully open source. We're launching the MVP at the end of this fiscal year, and that is in the beginning of September. So I recommend that you, again, I'll make these slides available. You can always contact me, and we can get you involved in this project, because we're hoping that it doesn't stay within just the Department of Energy space, that it becomes something that universities can use, that the Department of Defense can use, that other people can use in this space to find the data they need. So my last slide here is talking about some hidden obstacles. One of the most important has to deal with unintentional model poisoning. For those of you that are unfamiliar with model poisoning, it's when you intentionally, most of the time, feed incorrect data to a model in order to have it produce incorrect results. Now, thankfully, we don't have to deal with the intentional poisoning as much. We have a lot of security in place to hopefully avoid making bad data in the first place. But we do have unintentional poisoning, where we might have data that's not fully normalized, where we might have incorrect data, or data that needs more context for it to be valuable before it's fed into a model. Like, hey, we were running this with a certain machine on or off. And if that information's not included when we try to train the model, then we're producing incorrect results. And that's unintentional poisoning, because now we're generating models that are going to give us incorrect information. The feedback loop and dry, we talked a little bit about that to begin with. It has to do with, again, siloed projects. It's hard to get information out of individuals that have moved on in their lives or their careers. Sometimes they've retired, and so getting information out of them can be extremely difficult. And then data stagnation. The longer this data sits on a hard drive, the more information about it is lost. The information might stay around itself, but entropy, the law of entropy, says that we are going to lose something. And I think in a lot of cases, we lose the context around that data that we need. And so we know that we have a short amount of time from when that data is collected to get that context that's so necessary to our project and our program into Project Alexandria and into our system to make it a reality. And then the last part, again, is that equation. Classified data equals classified models, but unclassified data can also equal classified models. This is not a problem that anyone's really solved to at least the approval of the Department of Energy. We are working on things like flagging data sets to make sure they're not combined with other data sets. But then if you're flagging data sets with information that says, hey, if you combine these, you make them confidential, that information's confidential too. Everything's confidential, and it becomes a really hard problem to solve to help people understand, like, hey, you have to be really careful building AI and building anything that can make generative results or make these context connections in this space without making a problem and making them an issue and making things classified. Project Alexandria is designed from the ground up to allow for projects and ventures to, one, not have to worry about the long-term storage of their data. They just have to worry about how they get it to us. Once they get it to us with the proper context, we take care of it from there. And we are trying to work with the DOE on making a shared Azure tenant, because right now everything's separated between the labs. So we're trying to make a shared Azure and AWS tenant. We plan on federating. Right now we are only on the Azure Government Cloud and some HPCs, some high-performance compute clusters, like Oak Ridge and INL. But the plan is that we federate the storage onto multiple different clouds in order to facilitate all the needs of our customers. I am extremely grateful that I have the opportunity to work on such a big and important project in the non-proliferation space. And again, I'm very grateful to be able to have shared that with you today. So thank you all very much for attending my presentation.